Welcome back to ECE 501B. Homework 3 is due the night of our next meeting. We meet next Monday. Our first exam is a week from today, and there is review material available on the D2L website on the content page underneath in the unit exam number 1 material. Today, what I want to do is quickly explain the process that we will use for exam 1. If you've already looked at the material for the review, you maybe know what that will be. It should be consistent with previous semesters. The structure of the exam as far as what to maybe expect in terms of types of problems. And then we will actually, it's not here on the goal, but we will refresh where we left off last time with matrix addition and scalar multiplication of matrices and show that in fact that leads to a vector space, a particular matrix. Then we will talk about matrix multiplication. We'll illustrate how you might think of matrix multiplication differently if you've always thought about it being row times column, row times column. We'll try to give you a different perspective on how to think about what happens when you're multiplying two matrices together, what to maybe think or see when you're doing that multiplication. We will then look at some propositions or theorems related to maps that are invertible. That essentially is equivalent to saying that that map is both injective and surjective, or it's one-to-one and onto. If you have an invertible map, then it's injective and surjective. That leads us naturally into isomorphic vector spaces, which really says that these vector spaces are similar. They may not be the same vector spaces. One might be polynomials and another one might be R4, but they're isomorphic vector spaces. Then we will talk about operators, and that will not be Donald Trump in this particular class. It will be a linear map that, correct me when I'm wrong, has the same vector space as its input as it does for its output. That's an operator. It's operating basically on the same playing field. So if you've thought about a vector space as some place that you're living, you now have an operator. Well, that operator folds you back onto that same vector space, the output of that linear map. We're no longer thinking, if we talk about operators, about going from R3 to R2 or from R3 to R5. Now we're staying in, let's say, R3 with this linear map that's now called an operator. The process for exam number 1 is as follows. I'm just going to basically read this. You will be allowed 2 sheets of notes, and this will be a part of the notes that I provide for today's lecture, so you don't have to write it down if you don't want to. You can have a graphing calculator. I'm not sure that's going to do anything for you, but sometimes you just like to have that there. It's sort of like a security blanket or whatever you grew up with that you felt warm and fuzzy having. Now as engineers, we have a calculator, and we kind of view that in the same way. Something to write with, obviously, and then no on the others. No textbook, no classmates, no cell phone, and no computer or computers. So don't read this too literally. If you say, well, you said no computer, I brought 4. So no computers. I know how you guys try to interpret things, but that's what we're teaching in this class, isn't it? How to think critically and how to interpret everything. Did you say if, or did you say if and only if? Things like that. Is it injective? Is it surjective? Is it both? Those are important distinctions to keep track of. As far as what might be on the exam, probably there will be 5 problems. There'll be 1 proof. They won't all 5 be proofs. I know that that's where you feel the most comfortable, is with proofs, but we'll see how you do on one. You may have to demonstrate or show or produce a counterexample in certain problems. You might have to justify or explain by demonstrating or showing. You may have to create or build something, where that something might be related to vector space or a subspace or a direct sum decomposition. It might be basis vectors. It might be create a matrix that results from this linear map. And we've done that in the last lecture. You should be able to do that now. You may have to talk or create or demonstrate that something, or build an injective map, or a map that's surjective, or one-to-one, or onto, if you sort of think about those in their equivalent forms. Here's reviewing or starting where we left off last time, and we're going to use these last 2 points in terms of conventional matrix operations, which will allow us to build a new vector space. We can have all sorts of vector spaces. A vector space of polynomials that might be infinite dimensional, or it might be m-dimensional, Michigan dimensional, or it might be R6, or it might be something else that we've talked about. Well, now we will have a vector space as a result of these 2 kinds of operations on a set of matrices. And the set of matrices, so using matrix addition, which is element-wise, and scalar multiplication of a matrix, which just scales all of the elements in that matrix by the appropriate scalar, using those 2 operations with the set of matrices, then this matrix, defined as m comma n on the field F, meaning all of the elements in the matrix that's m rows by n columns in dimension, come from F, and in here we're using F to be either R or C. That could be real numbers or complex numbers. That set of matrices with matrix addition and scalar matrix multiplication forms a vector space. Meaning, what do you have to have for this vector space? Or what are some things that you might think have to be true for a vector space? Well, think first maybe about a subspace, but now the vector space has these properties that it needs to house or to satisfy. One of those is closed under addition. If you have a 2x7 set of matrices, if you add matrices from that set together, you end up back in that set. It's closed under addition. It's closed under scalar multiplication. It forms a vector space. The dimension, or the size of that vector space, is 2 times 7, or 14. It's like R14. It's just now that those 14 elements are in a particular location of your 2x7 matrix. That's assuming in a particular example where Michigan is 2 and Nevada is 7. And I don't know if that was the football score or not, but somebody got a safety and somebody had a touchdown with an extra point if it was a 2x7. Sorry. Almost thought maybe it wasn't a football score because of the 2, but then I remembered you could have a safety to generate a 2. I was going to say maybe their soccer teams played. Be kind of an out-of-hand soccer game, wouldn't it? 2 to 7, 2x7. And you probably don't have a 2x7 at Home Depot. You might have a 2x4 or 2x6. But you can have all sorts of matrices. But once you're in that set, that's now where you're living for your vector space. We've talked about matrix addition. We've talked about matrix multiplication by a scalar. Now let's talk about multiplication of matrices. Multiplication using the matrix representation, that's that script M on the linear map T, from, let's say, vector space V to vector space W. Sometimes it makes sense, or it's possible to concatenate these operations or perform these one after another. Suppose that we have a linear map that maps from U to V, and then after we apply that, we use the linear map S from V to W. It would be nice if we went through that composition of linear maps if we could get the same result by doing matrix multiplication on initial locations in, let's say, a particular vector space U ending up in W. It would be nice if this composition of T then S, as far as a linear map, was consistent with the matrix that we found from T and the matrix we found from S if we found the product of matrix of S times matrix of T gives us the same result that we have progressing through those linear maps. But we also know that matrix multiplication, or these even linear maps, may not commute. You know that if you even if these matrices would be compatible with each other, and by compatible I'm meaning the columns of the leftmost matrix in the product is equal to the rows in the rightmost matrix in that product. That's a compatible set of matrices. Even if you have that, the other orientation of those matrices may not work. It would be nice, and this is what we were hoping would be the case. If you found the matrix that results from taking the linear map T and then operating on that result with the linear map S, is that equivalent to the matrix of T pre-multiplied by the matrix S? And it is. If we use the matrix multiplication or the matrix representation that we talked about last time, building that up, and that depends, what's your matrix representation depend on? If I give you a script M of T, what else was in the argument of that script M? That's another way of thinking of it. The basis vectors. The basis vectors for your domain, the basis vectors for your codomain. The matrix representation is hinging or depends on those bases. Typically, we don't identify those bases, and they may just be the standard bases. And then we just say the matrix representation of our linear map T. You'll be pleased to know that we're not going to talk about matrix multiplication in the normal way. Row times column, row times column. I think you know that. I'm assuming that you can review that if you need to. What I want to do, though, is think about matrix multiplication in a different way via an example. Suppose that we have a matrix that is 3 by 3. The first column is 1, 5, 7. The second column is 6, 2, 1. And the third column is 4, 5, 3. Let's say that's our A matrix. Then suppose that we post multiply that by the following: 1, 0, 0, 2, 0, 1, 0 minus 1, 0, 1, 1, 0, 1, 0, 2. And that's now maybe B. Now, what I want us to be able to do is quickly write down the result. Did everybody get that written down? And how did that happen? Or how can I just sort of quickly write down that product? This is now a 3 by 3 times a 3 by 5. Where did that come from? We're going to have a answer that's 3 by 5. How was I able to sort of quickly write, I mean, was I doing row times column, row times, because if you did it the normal way, you would say, okay, this first column in the answer is going to be this times this. That's which element? That's just that element. Then the next element was this times this. That's that one. And then the last one, I'm run out of highlights, but I'll do another one here by that, and that's this one. The way that I want you to be thinking about this, a different way, instead of having to do those 3 row by column, is to look at the row that you are, I'm sorry, the column in the second matrix. That's 1, 0, 0. What is that really doing? Well, that's scaling each of the 3 columns in the first matrix on the left, A, by the scaling amount indicated in each row. Meaning the 1, 0, 0, the 1 is going to weight the first column, the 0 is weighting the second column, and the third 0, or the 0 in the third row, is weighting the third column. Which means that that very first column, when I multiply it out, is really just going to copy over the first column in A. Is it 1, 5, 7? That's just a duplication of the first column. The easier one, another easy one to think about is this one. If we use that same thought process, what's this third column in our result going to equal? We're not going to weight the first column. We're not going to weight the third column. All we're doing is changing the sign in the second column. This is going to say, okay, take the second column, or let me write this out. Let's say that this is going to say the negative of second column of A. And in that sense, then, the third column in our product, or in the answer, should be -6, -2, -1. If we go to some of those that maybe aren't as easy to write down, let's go to the fourth column. That's just adding the first 2 columns in A, because we take the first column and scale it by 1. We take the second column and scale that by 1 and add them together. So we should have 7, 7, 8 for the fourth column in our result. Have you seen this before? Have you thought about matrix multiplication this way? It's a nice way to think. And what does this tell you? This tells you that the result, all of those columns, all you're going to do is find answers or results that are linear combinations of those 3 columns in A. You can't get anywhere else than those linear combinations of the columns in A by post-multiplying by any matrix that's 3 by whatever. And you might check my work in the 5th column. What should that be? That should be the first column plus 2 times the third column. So it's 8 plus 1, or 9. It's 10 plus 5, or 15. It's 6 plus 7, or 13. And the only one we haven't done is the second column, which should be twice the first column plus the third column. And that should be 6, 15, and 17. Told you. Keep me honest. That's why you didn't know where that was coming from, right? That one element that was throwing you. You thought this must be the new map. Is it okay how to think about that? And you could do just the opposite. Sometimes it's easier and you're sort of looking for, are my columns in the rightmost matrix somewhat sparse, or are the rows in my leftmost matrix somewhat sparse? Do you see that a dual way of thinking of the product could be, oh, let me take 1 times the first row of B plus 6 times the second row of B plus 4 times the third row of B to generate the first row of your result. That's not as easy for me to think about, but if A was more sparse, meaning had more zeros, it might be easier to think about combining rows than manipulating columns. I still think I think better in looking at columns than rows, but you can do it either way. And that's what I wanted to cover relative to matrix multiplication. You can think of matrix multiplication as combining columns or combining rows, depending on how you want to put those together. A few more things about matrix multiplication. The standard matrix multiplication maintains the properties that we want. By that, I mean, one, if we are given, let's say, an A matrix that's R raised to the m by n, is it clear what I mean by that? The matrices A are matrices. What are the dimensions on A? Has Michigan rows and Nevada columns. And what are the elements in those matrices? They're reals. That's what that means. So A is in that set. And if B is from the reals, let's say it's J by L. So you don't think that I'm trying to do the square root of -1. That's a capital J and not a lowercase j. And ECE, you never know what J is going to be, or I. The product AB is only defined under what condition? We need Nevada to equal Jersey. Didn't know what I was going to. Is there a state that begins with J? Should have used a different superscript, huh? So that we could continue our geography lesson in ECE 501B. That's equivalent then, this constraint that Nevada is equal to Jersey, that's equivalent to the requirement that the output space of one map must be the input space of the other map. In that sentence that I just wrote, which matrix's output space am I interested in being the same as which matrix's input space? Which matrix am I thinking of on the output space? Is it A? You want the output of B. You want to take that output, the result that B gives you, that has to be the input space of A. So think of a vector, let's say, post-multiplying B. That vector needs to be L rows tall and 1 column wide. But the result of B times X, where's that going to map you? Into what space? That'll be the output space of B. And that's going to be this J-dimensional space. That needs to be equal to the input space that A is expecting. So if you were shaking hands or if you were doing some kind of exchange, you need the output from B to be compatible with the input of A. So things are sort of coming from right to left, and that's not really how we might read that matrix product. But I want you to be clear on what we're meaning when we say the output space of one map must be the input space of the other. Here, the one map is B, the other is A. Another property that we want to maintain is the following. Even when the multiplications are defined, in general, we know that the matrix representation of the linear map T operating on the matrix representation of the linear map S, how does that relate to, in general, the matrix multiplication of S and T? Those are not the same, are they? Matrix multiplication may not commute. The matrix of T times the matrix of S is probably not going to equal the matrix of S times the matrix of T. I've already told you what I want you to be comfortable with. Here, this was just dealing with matrices, but there's nothing to keep us from saying that that matrix B could actually be little l, Louisiana, might be a 1. If that's the case, then B is a vector. So we have actually a proposition that tells us that what we've been talking about still works when we have a matrix vector product. Meaning, in proposition 14 in chapter 3, if we are given a linear map T that's now mapping from V to W, and suppose that the set of basis vectors on V are these vectors V1, V sub 2 up to V sub n, and the basis on W is, let's say, W1, W2 up to W sub m, then the matrix representation of TV is the same as the matrix of T times the matrix of V, where V now may be a linear combination of the lowercase v's, the basis vectors on capital V, and T is mapping from that domain into the range that's spanned by those lowercase w vectors. And that shouldn't come as a surprise. Now, let's talk about another topic, which is a linear map again, T from V to W is said to be invertible if there exists a map let's say S, and what's the domain of S if it's going to be the inversion of the linear map T? It now is going to be mapping what was the codomain into what was the domain, W to V, such that ST is the identity map, which we might just label as I, or TS is likewise the identity map. So that's what we mean by a linear map being invertible. It has another map, S, such that concatenating S onto T or T onto S gives us the identity map. We can then create a definition from that statement, a map S such that ST equals the identity map and TS equals the identity map is the inverse of T. That's our definition of the inverse. And we usually like to keep them, the inverse and the linear map, somewhat connected, and we can do that by saying if the inverse of T exists, then it's unique and we give it the symbol T inverse. Let's now look at a proposition for a linear map being invertible. Proposition 17. A linear map is invertible if and only if that map, or it is, injective and surjective. Now, we're not going to go through the formal proof. I'll let you look in the textbook for that. But let's now sort of talk about it intuitively, what we mean by an invertible map and why is it necessary and sufficient for that map to be both injective and surjective. So you can see Axler for the formal proof. For now, let's examine this proposition, proposition 317, on a more intuitive level. Suppose that we're given a linear map, T, that's mapping from V to W. If that linear map, suppose T is not injective. So if T is non-injective, what does that mean? That means it has a non-trivial null space. What does that mean? If you have a non-trivial null space, what does that allow you to do? Let's say if you were creating some examples and giving them to a colleague. Okay, so now you can map multiple input vectors to the same output if you have a non-trivial null space, and you do if your linear map is non-injective. If T is non-injective, then multiple vectors in our domain, or in the vector space V, map to the same vector in W. Now, I've been sort of in a teasing manner. My other class, we're studying about complex power, and we have this complex power triangle, and I talk about, do you see the hypotenuse? And I say, I hope no one's listening in the hallway, because we were all saying, I see a hypotenuse when we started talking about what's the apparent power. Now, do you see a diagram that illustrates this? When you say, oh, T is non-injective, I sort of want you to be visualizing what that might mean in a picture. We're very visual. So just reading that and saying, oh, the map's non-injective, it's like, I don't know, okay, it's non-injective. Okay, we have multiple input vectors that go to the same point. What's that look like in a picture? Can you diagram that? What does that look like? Looks like a black hole. Do you start seeing clouds? So I'm not even going to give you a cloud. I don't want to make this very cloudy. But I do want you to sort of start to see this. Meaning, This V1 could be in the cloud, couldn't it? It could be in the domain V, capital V, and maybe you have another vector in that same cloud, V sub 2, but if they are related by some combination of vectors in the null space of the linear map T, then V1 and V2 are going to map to the same point in our second cloud, or in the codomains vector space W, meaning they will go, luckily this is not being video recorded, it's just capturing the screen. So unfortunately, those of you that are listening to this don't get the benefit of some of my miscues in front of the class, where I'm trying to put on imaginary glasses. What I'm saying is this will now, if V1 and V2 differ by a linear combination of vectors in the null space of the linear map, then if we mapped V1 through T, and if we mapped V2 through T, they are both going to end up at the same point in the cloud of our codomain, capital W, which I'm representing as W1. And that's the image that I'm hoping you start to see when you say, oh, T is non-injective. Think of this map. I could have multiple vectors going to the same point through that linear map. What does that mean relative to the map being or not being invertible? It's going to be very difficult to try to get an inverse from that, isn't it? Because it's going to be impossible to say, oh, I know that W1 produces V1. Somebody else is going to go, no, that W1 produces V2. How are you going to know? You're not. It's going to be impossible to have an inverse of that linear map T. Why? Because that linear map T had it was non-injective. It had a non-trivial null space, that linear map T. Here, let me write some comments down. Remember, a linear map requires a unique output for a given input. Is that obeyed in the picture above? Is T a linear map? T is a linear map. A linear map requires a unique output for a given input. Is that still okay? Yes. We didn't say anything about that output being unique. I'm sorry, distinct, did we? V1 gives us a unique output, W1. V2 gives us a unique output, W1. It's the same output. We didn't say it has to be distinct. In the above picture, there's no way the inverse map S, which would try to map from V to W, can exist since it would have to map the S map, would have to map a single vector in our codomain, or in our original codomain W, to multiple vectors in V. And there you could say, okay, S can't be a linear map then. because of the first sentence. A linear map requires a unique output for a given input. Now we're giving S an input W1. It can't have a unique output if it was a linear map for this case. So you could sort of view this from two different ways as far as that diagram. All right, that's one of the intuitive ideas behind an invertible map being injective. Let's look at the other piece, which is surjective. And here we tried to convince ourselves that the map has to be injective. We have to have a trivial null space for that linear map. That's one of the conditions. It has to be injective. What if the map, let's say if T is non-surjective, now what do we have? Then there are vectors in our codomain in W which are not produced or they aren't generated via the linear map T from V. If T is non-surjective, that means T is not going to cover all of W. If T is non-surjective, then there are vectors in our codomain which are not produced by T acting on the vectors of V. But the inverse map, S, that takes us from W to V, what's it going to do with those vectors in W that we haven't covered or haven't reached? It doesn't know what to do. It would have to ignore those. How's it know to do that? It doesn't. But the inverse map S from W to V would have to ignore those elements of W. And there's where we run into problems. But a map acts on all elements of a space. Do you see how we could maybe show that with a diagram? Or with, you guys seem to like the clouds. Let's go back to the clouds. Here, they always accuse us of having our heads in the cloud. Well, now there's all sorts of things in the cloud, right? You need to learn how to create things from data in the cloud. And that's what this course is going to help you start to better understand or appreciate. We're now looking at it from this set of clouds. Here is our domain. There's our codomain. If I have a non-surjective map, what does that mean? Pictorially. Pardon? Okay. The domain, the comment from the class was that the domain, the vectors in the domain will only go to a limited location or area in W in this diagram. So let's say, well, maybe what I better do is suppose that I now say, okay, I go here and I go here, and it's not necessarily the same point, but now what was stated, which is correct, is now maybe that is, and what is this called? This is T. This is now the range of T. And there could be, and there are, if our map is non-surjective, there are other vectors in our codomain that aren't covered by this linear map T from V, which means that these S would ignore. And it's kind of, how would you do that? That's why it has to be a surjective map. So you need it to be 1-to-1, which is injective, and it has to be, and the 1-to-1 now means what? You have a trivial null space. You have one vector in the domain mapping to another vector in the codomain. It's 1-to-1. It's onto, meaning that you cover you're onto the entire codomain. Then you can go back. Let's look at some other facts relative to invertibility. Using our earlier results, we know that no map to a lower dimension can be what? So no map to a lower dimension can be, now I'm looking for injective or surjective. So now we're going from a bigger dimension to a smaller dimension. And if that's the case, if we have a map that's going from a big to a small, what do we know about that map? It can't be injective, can it? No map to a lower dimension can be injective. And that was corollary 3.5. What does the matrix representation of this statement look like? And this is what I think you should start to visualize. What's the matrix representation of the linear map T that's going from a big dimension to a small dimension? What does that look like? And now what I'm going to be saying is it tall and skinny, or is it short and wide? Is it the first one or the second? And I don't remember what I said. Is the matrix representation of 1? We're going from big to small. What's the output? Small, right? The output is the rows. The input are the columns of our map. So this is going, or the matrix representation of 1 looks like short and wide, right? So this matrix-wise looks like that. And that, when you see that matrix, you know you have a non-trivial null space. This is a non-injective map. That's corollary 3.5. We know no map to a lower dimension can be injective because we now have a non-trivial null space. The other corollary related or similar to that, just the opposite, is no map to a higher dimension now I feel like we're in Star Trek or something. No map to a higher dimension can be what? Surjective. And that was corollary 3,6. And now do you see what that map looks like? Now we're going from a small input domain to a big codomain. Now the matrix should be tall and narrow. The matrix representation of that linear map. Do you see that? That's a non-surjective. We can't cover all of those coordinates in those rows by what? Starting with such a tiny input space. We have no way of making all of those coordinates fill the output space or the codomain. What's that telling us? Hopefully now we see that inverses only exist for maps between spaces of equal dimension. We need, in order for us to have invertible maps, we need those maps to at least be the same number of, or the input space needs to be the same dimension as our output space. What does this look like in terms of a matrix representation? Here's the question. What does this mean in terms of matrix representation? The matrix has to be square, right? We said it can't be short and wide, and it can't be tall and narrow. It has to be square. So the answer to that question is that the matrix representation must be square. So a pseudo-inverse is when you do have a linear map that is not square. Then you might have more columns than you have rows, or you might have more rows than you have columns. And now you're trying to do the best you can with what you're given. So now a pseudo-inverse is trying to do the best job it can in inverting the information that it's given. But you can sort of see the difficulties that you could run into with these not having square or consistency between your input space and output space on these linear maps. And a pseudo-inverse is when you don't have an inverse. You have a pseudo-inverse, and that in the easiest way to think of that is, let's just say that our linear map is not square. You could have a square linear map that's not invertible. And why is that? You may have some dependency in your rows or columns, which means you might have a non-trivial null space. And if you have a non-trivial null space, then you definitely don't have a surjective map either, if you have a square matrix. to fill this out just a little bit, if we look at the columns, of the matrix representation of T, we are looking at TV1, TV2. Remember how we were creating these matrix representations? We were looking at these maps on these set of basis vectors, V1 through Vn, and those were expressed in terms of the basis vectors in our codomain. So the columns TV1, TV2 up to TVn expressed in terms of W1, W2 up to W sub n. And in this case, the only way that we can have the same dimension in our domain and codomain is to have the same number of vectors in our basis. So we have the same dimension only if Nevada is equal to Michigan. And that really says then that we have the same number of columns, or the number of columns equals the number of rows. Which gives us our square matrix. And that then says that only square matrices have an inverse. If that's the case, now that we could sort of be thinking about having an inverse between two vector spaces, now we can talk about this concept of isomorphic, which you could sort of just say, oh, that means similar. So the same shape, isomorphic. Two spaces are said to be isomorphic if there is an invertible map I should say invertible linear map between the spaces. Two isomorphic vector spaces have the same properties. And another way to think of that is provided in Theorem 318. That says, and now we're back to tweeting, which you know what that means. We have two finite dimensional vector spaces, which is now FDVS. Two finite dimensional vector spaces are isomorphic if and only if those two vector spaces, they have the same dimension. Now, how would we prove that? or what's maybe a key word to look at in that theorem or in that statement, and now that might guide our proof. What's a key word in that two finite dimensional vector spaces are isomorphic if and only if they have the same dimension? The key word is not even a word, I guess. It's the if. The if and only if in that theorem. That says that we need to show it in both directions. Meaning, can we show that if we have two finite dimensional vector spaces that are isomorphic, can we show that they have the same dimension? Or if they start with the same dimension, can we show that those two finite dimensional vector spaces are isomorphic? Our proof, then, we need to prove in both directions. One, let's assume that V and W are isomorphic finite dimensional vector spaces, which means now we need to show that they have the same dimension. By definition of isomorphic, what did we mean when we said isomorphic? That said we had a invertible linear map between those vector spaces. By definition of isomorphic, this means there is an invertible linear map T. Our linear map T has to be invertible, meaning there has to be a T inverse. But what does a map being invertible mean about that map? So before we say anything about the same dimension, let's just go back a little bit further to one of the first things we talked about today about if I have a map that's invertible, what else does it? It's invertible if and only if it's one-to-one and onto, or injective and surjective. So let's now say that invertibility, or the fact that it's invertible, implies injective and surjective. And now we go back to this sort of long and wide, or I'm sorry, short and wide and tall and thin, or tall and narrow. No linear map is injective to a finite dimensional vector space of bigger or smaller dimension. So now if you have a linear map, if it's injective, can't be going to a smaller dimension. It can't be short. So this is now saying smaller. But what do we know about our maps? We're going from V to W, and we want W to not be any smaller than V, right? So this says that we need the dimension of where we started to be at least or less than or equal to the dimension of where we're going. That's the implication of a map being injected. We can't be going to a smaller dimension, which means where we're going, the codomain needs to be bigger dimensionally than the domain, at least as big. What about the other direction? No linear map is surjective to a finite dimensional vector space of blank dimension. Now, if we want our map to be surjective, it can't be going to a larger dimension. And what does that imply? Relationship between the dimension of V and the dimension of W. Now we know that the dimension of where we're headed needs to be less than or equal to the dimension of where we started. We can't get larger. All right, now let's just order those appropriately. Let's say that we start with the first one. Dimension of V is less than or equal to the dimension of W, but the second relationship said that the dimension of W was less than or equal to the dimension of V. Ouch. What's that saying? Now we've squeezed the dimension of W between the dimension of V. They have to be the same. Therefore, the dimension of V is equal to the dimension of W, and that's what we set out to show in our first direction. We assumed our map was isomorphic, or I'm sorry, we assumed our two vector spaces were isomorphic, and we just showed that they have to have the same dimension. Now let's look at the second direction. To assume that the domain and codomain have the same dimension. The dimension of V is equal to the dimension of W. And now let's take our basis vectors. V1 to V sub n as basis on V, and W1 through W sub n as basis on W. Now let's look at a particular map. Consider the particular linear map T of A1V1 plus A2V2 plus A sub n V sub n, and let's say that's equal to A1W1 plus A2W2 plus A sub n W sub n. Or if we use the homogeneity property on that linear map, we're really saying, in other words, TV1 equals W1, TV2 equals W2, etc. TVn is equal to W sub n. This definition meets additivity and homogeneity. So it's a valid linear map. Now what we do know is any vector in W can be created through the appropriate choice or choices of these A sub i's. Or that is, the W sub i's actually span W. If those W sub i's span W, what does that tell us about the linear map T? T is where we want to go. That's the codomain, and now we can span that entire space because we found a basis on that, and we can combine those any way we want. T is actually surjective by that representation. Or the T V sub L's covers all of W. Now, what we need to show is the next. So we've shown that it's surjective. We can actually show that it's, we've shown that it's surjective. Now we need to show with the same implication, which is here, we can show that it's injective. We could say, when is the right side equal to 0? Only when all the A's are equal to 0, because you know the W's are linearly independent because they're a basis. Well, if the right-hand side is 0, what's the argument of the T? If all the A's are 0, it's 0. So now you know T of 0 equals 0. That's the only vector in the null space of T. It's a trivial null space. That map is injective, and now we've concluded the other direction. Maybe I'll write that down in the notes, but I sort of talked my way through it. We're out of time. Thank you for being patient, and we'll pick up somewhere, probably with operators, as promised, on Monday.